Bismillahirrahmanirrahim. Assalamu alaikum students. This is your first lecture of physics. In this lecture, I am going to discuss simple harmonic motion and its characteristics. It is a topic of chapter number 10th of 10th class. In this chapter, we are going to discuss simple harmonic motion, examples of simple harmonic motion, important characteristics of simple harmonic motion, and damped oscillation. Now I am going to refresh your knowledge and I am going to tell you about vibration, which is a key to understand simple harmonic motion. A body is said to be vibrating if it moves back and forth or to and fro motion of a body about its mean position. As you can see the example of a simple pendulum, the pendulum starts vibrating about its mean position O. Now I am going to tell you the definition of simple harmonic motion. Simple harmonic motion occurs when the net force is proportional to the displacement from the mean position and is always directed towards the mean position. In order to understand the simple harmonic motion, we are going to discuss few examples in detail. That motion of mass attached to a spring, ball and ball system, motion of a simple pendulum. Now we will discuss it individually in detail. In order to understand simple harmonic motion, I am discuss its first example, that is mass attached to a spring system. In this, I am going to take a mass M whose one end is attached with the one end of the spring and other end of the spring is attached with a rigid support. As the mass is placed on the frictionless horizontal surface, and now by applying an external force on the mass, we are going to extend this mass from its mean position O to an extreme position A. Then according to Hooke's law, this force is directly proportional to the change in length of the spring. Now we know from Hooke's law that F is equals to minus kx, where k is known as the spring constant, x is the displacement that is covered by the mass m. The negative sign indicates that the force exerted by the spring is always directed opposite to the displacement of the mass. Now we can find out the value of the spring constant, that is k is equals to F by x. Now I am defining spring constant, that is the ratio of external force acting on the spring to increase in its length is called the spring constant and its unit is Newton per meter. Also we know that the spring force always acts towards the mean position. So it is sometimes called as a restoring force. You should know about the restoring force. A restoring force always push or pull the object performing oscillatory motion towards the mean position. Now in order to understand the example of simple harmonic motion, we are going to discuss it in detail. Initially, when the mass M is at rest in the mean position O, and the resultant force on the mass is 0. Suppose the mass is pulled through a distance x up to the extreme position A and then released. The restoring force exerted by the spring on the mass will pull it towards the mean position. Due to the restoring force, the mass moves backwards, the mean position O. The magnitude of the restoring force decreases with the distance from the mean position and becomes 0 at the mean position O. However, the mass gains speed as it moves towards the mean position and its speed becomes maximum at mean position O due to inertia of the mass. Similarly, it will continue its motion and reaches the extreme position B. As the mass moves from the mean position O to the extreme position B, the restoring force acting on it towards the mean position steadily increases in strength. Hence, the speed of the mass decreases as it moves towards the extreme position B. The mass finally comes to rest at the extreme position B for a fraction of seconds. And then again it will return to the mean position due to the restoring force. This process is repeated and the mass continues to oscillate back and forth about the mean position O Such motion of a mass attached to a spring or horizontal frictionless surface is known as simple harmonic motion. Now the few important points arises. At point O, when the mass m reached at point O and we hold it for a fraction of seconds before releases the mass, it covers a maximum distance from point O to A. So its acceleration is maximum because displacement is maximum at that time. And as the mass is at rest position, so its velocity is 0. At the same time, it gains a new position from its mean position. It moves from mean to extreme position. So its potential energy is also maximum because potential energy is change in position. As we know, at point A, the mass is not moving, so its kinetic energy is 0. Now we will discuss the same points on O. At O position or mean position O, acceleration is 0 because distance covered by the mass is 0. What happens with the velocity? Velocity is maximum due to the inertia in the mass. What about the potential energy? Again, due to the change in position. As we move the mass from the point O to A and it again reaches the point O, so there is no change in position right now. So potential energy is 0 here. What about the kinetic energy? Due to inertia, as its speeds increases, so kinetic energy is maximum. Now at point B, the mass finally comes to rest for a fraction of second and its velocity becomes 0 at that point. Similarly, when velocity becomes 0, its kinetic energy is equals to 0. And when it moves towards the point B, once again it covers a distance x in the backward direction. So its acceleration is maximum. As it changes its position from point O to B, so its potential energy is also maximum. As this process is repeated and the mass continues to oscillate back and forth about the mean position O, such motion of a mass attached to a spring on a horizontal frictionless surface is known as simple harmonic motion. And the time period for the simple harmonic motion for a mass attached to a spring system is T is equals to 2 pi under root m by k, where m is the mass of the object and k is your spring constant. Now the next example is the motion of a ball placed in a ball, another example of simple harmonic motion. Now as you can see in the picture that when the ball is at the mean position O, that is at the center of the ball, net forces acting on the ball is 0. In this position, weight of the ball acts downward and is equal to the upward normal forces of the surface of the ball. Hence, there is no motion. And if the ball is bring to a position A, as you can see in the figure, and then release it, the ball will start moving towards the mean position O. Due to the restoring force caused by its weight at position O, the ball gets maximum speed, and due to inertia, it moves towards the extreme position B. While going towards the position B, the speed of the ball decreases due to the restoring force, which acts towards the mean position. At the position B, the ball stops for a while and then again moves towards the mean position O under the action of the restoring force. This to and fro motion of the ball continue about the mean position O till all of its energy is lost due to friction. So, to and fro motion of a ball about a mean position placed in a ball is an example of simple harmonic motion. Once again, we are discuss all the 3 points at point A, at O, and at point B. At point A, when the ball is going to be picked up or pulled towards the point A, it covers a distance x from mean position towards extreme position. So, As distance is maximum, so acceleration is maximum. As we hold the ball for a fraction of a second, so its velocity is 0. When its velocity is 0, its kinetic energy is 0. And as we see that it covers a certain height, it is at a height, so its potential energy is maximum. Now we release the ball starts rolling towards its mean position. When it starts rolling down, it decreases its height, and when it reaches at point O, its height becomes 0, so its potential energy is 0, and due to inertia, it will gain the speed, its velocity is maximum, and its kinetic energy is also maximum. As we start moving that ball from position O, so at position O, its acceleration is 0 because the distance covered at point O is equals to 0. Now at point B, what happens? When the ball reach at point B, for a fraction of a second, it will stop. When it will stop, its velocity is equals to 0. Its kinetic energy becomes equals to 0. And as it covers certain height at point B, so its potential energy is maximum. And as we know, as we can see that the height is maximum, the distance covered is maximum, so its acceleration is also maximum. So this to and fro motion of a ball continue about its mean position till all of its energy is lost due to friction. So this proves that this is also an example of simple harmonic motion. Now we will move towards our next example. Now we will move towards another example, that is a simple pendulum, which is also example of simple harmonic motion. As you can see in the figure that it consists of a small bob of mass m suspended from a light string of length L fixed at its upper end. In the equilibrium position O, the net force on the bob is 0 and the bob is stationary. Now, if we bring the bob to an extreme position A, the net force is not 0. There is no force acting along the string as the tension in the string cancels the component of the weight, that is mg cos of theta. As you can see in the figure that this bob's weight is going to be divided into its two components, mg cos of theta and mg sin of theta. Hence, there is no motion along this direction. The component of the weight mg sin of theta is directed towards the mean position, as you can see in the figure, and acts as a restoring force. Due to this force, the bob starts moving towards the mean position O. At O, the bob has got the maximum velocity, and due to inertia, it does not stop at O. Rather, it continues to move towards the extreme position B. During its motion towards point B, the velocity of the bob decreases. Due to the restoring force, the velocity of the bob becomes 0. As it reaches the point B for a fraction of seconds, the restoring force mg sin of theta still acts towards the mean position O. And due to this force, the bob again starts moving towards the mean position O. In this way, the bob continues its to and fro motion about the mean position. Therefore, the acceleration of the bob is also directed towards O. Similarly, when the bob moves from O to B, its speed decreases due to restoring force, which again acts towards O, which is the mean position. Therefore, acceleration of the bob is again directed towards its mean position O. It follows that the acceleration of the bob is always directed towards the mean position O. Hence, the motion of a simple pendulum is also an example of simple harmonic motion, and it also covers all the features as the above discussed example have. That at point A, its acceleration is maximum because its distance is maximum from the mean position. Its velocity is 0 because bob is at rest, so its kinetic energy is also 0. Its potential energy is maximum because height is maximum from the surface of the earth. At point O, The bob comes to its initial position O. So distance is equals to 0, acceleration is equals to 0. Velocity is maximum due to inertia. Potential energy is 0 as the height covered by the bob is 0. So potential energy is 0. As velocity is maximum, so kinetic energy is also maximum. At point B, when the bob reaches at the other extreme point B, it stops for a fraction of second. For that time, its velocity is 0. As velocity becomes equals to 0, its kinetic energy is equals to 0. And it gains a maximum height, so its potential energy is maximum. As the height is maximum or the distance is maximum, so acceleration is also maximum. This shows that the acceleration of the bob is always directed towards the mean position O. Hence, the motion of a simple pendulum is simple harmonic motion. The time period of simple harmonic motion for a simple pendulum is t is equals to 2 pi under root L by g, where L is the length of the pendulum and g is the gravitational acceleration. Now we will discuss all the important features or the points of simple harmonic motion that we have already discussed in all the above examples. Number one, that a body executing simple harmonic motion always vibrates about a fixed point. Number two, its acceleration is always directed towards the mean position. Number three, the magnitude of acceleration is always directly proportional to its displacement from the mean position. That is, acceleration will be 0 at the mean position, while it will be maximum at the extreme positions. Similarly, its velocity is maximum at the mean position and 0 on the extreme position. These are the all points that we have discussed in all the three examples. Now I am going to discuss the last topic of today's lecture, that is damped oscillation. What actually are the damped oscillations? The oscillation of a system in the presence of some resistive force are called damped oscillation. Whenever body starts to move about its mean position or performing a to and fro motion about its mean position, it experiences some resistive forces, and these resistive forces are responsible to slow down its motion, and eventually the body stops. In all the systems, force of friction retards the motion so that the system do not oscillate indefinitely. The friction reduces the mechanical energy of the system. As the time passes and the motion is said to be damped, the damping progressively reduces the amplitude of motion, as you can see in the diagram, that a body oscillating initially, its amplitude is more than 0.5 and slowly it starts to decrease. And this is the graphical representation of damping oscillation. Now for your practice, I am going to give you some creative questions related to this topic. Few are simple, few are tricky, but I think after having this lecture, you are able to attempt all the questions. For example, what is simple harmonic motion? What are the necessary conditions for a body to execute simple harmonic motion? You can think several examples in everyday life of motion that are simple harmonic motion other than these three examples. What are damped oscillations? And few conceptual questions. Likewise, if the length of a simple pendulum is doubled, what will be the change in its time period? A ball is dropped from a certain height onto the floor and keep bouncing. Is the motion of the ball simple harmonic motion? Explain it. And I'm going to give you few numericals which are related to this article, that is 10.1, 10.2 of the exercise, 10.3, 10.4. All these four numericals, you can do it by using these two formulas, that is t is equals to 2 pi under root m by k and t is equals to 2 pi under root L by g.